In this video, we are going to look at an example of how you would do a calculation for a titration. First, you have to understand what a titration is, as I've got typed here. A titration is when you take a solution for which you know the concentration and you gradually, slowly add it to a second solution that doesn't have for which the concentration is not known. And you gradually add the known solution to the unknown. You will get to a point where the reaction is complete. Usually this will be determined by maybe a color change of an acid-base indicator, by a pH probe that's monitoring the pH, or in the case of redox reactions, a lot of times one of the chemicals involved in the reaction has a different color when it has a different oxidation state. So you'll see that change in color as the indication of completeness. Titration sounds like something really fancy, but it's really just an application of stoichiometry, because once you know the amount of the known concentration and you know its concentration, you can calculate the moles of that chemical. And once you know moles of one chemical, you can use a balanced chemical equation and the mole ratios to figure out the amounts of the other chemicals. Titration, as I mentioned, can be used for acid-base reactions. It can also be used for oxidation-reduction reactions. So I'm going to go through a little example here. This is a oxidation-reduction reaction. I picked this one because it was a little bit more complicated equation. So you see a little bit more complicated mole ratios in the balanced chemical equation. Usually the coefficients on a redox titration are going to be a little bit more complicated. But in this case, so we know in this problem we would know something about one of the chemicals. We would know its concentration and its amount. In this case, in this problem, I was told that there were 22.5 milliliters of potassium permanganate. So I was given the volume of potassium permanganate, the amount, and I'm also given the molarity. So I'm going to use molarity as a conversion factor to convert volume into moles so that I can use mole relationships in the BCA table. First, I've got to convert milliliters to liters, so there's 1,000 milliliters in a liter. And then the concentration of the potassium permanganate that I know in advance is 0.374 molar, which the capital M really just means moles in every 1 liter. So when I take 22.5 divided by 1,000 times 0.374, I get that I have 0.008415 moles of potassium permanganate. So I'm going to use that amount in my BCA table for potassium permanganate. The chemical whose concentration I want to know, that I do not know, is hydrogen iodide. So I'm going to go through and I'm going to fill out the entire BCA table just to give you some extra practice with mole ratios. Now, if you were doing this for a multiple choice question on an AP chemistry test, I would not expect you to do that. I would encourage you to think of faster, quicker, easier ways to do it. But just because I also want you to practice this type of thinking, we're going to go ahead and do the whole thing. So I'm going to set up my BCA table. The potassium permanganate is 0.008415 moles. So I'm going to use some mole ratios to figure out the other parts. The ratio of hydrogen iodide to potassium permanganate is 10 to 2. So there are 5 times as much hydrogen iodide as there is potassium permanganate. So I'm going to take that 0.008415 and basically multiply it by 5. So all of that is going to get used. I know that because I measured, this came from a measurement in the lab where we used all of it. And I need 5 times as much. So I'm going to take that and multiply by 5. And I'll get 0.04208. If you're curious about the XS notation, it just means that we have enough hydrogen iodide. We have at least 0.04208 moles. So we have more than enough. Just to go ahead and practice the other mole ratios, the ratio of potassium permanganate to sulfuric acid is 2 to 3. So using that ratio, the change line, the amount of sulfuric acid that would be used is 0.01262. The change line is really what you're figuring out when you're doing a BCA table. Before the reaction, you will not have any product. After the reaction, during the reaction, product's going to be formed, so all of these are going to be added. We're creating a certain amount of each of these chemicals. And you can compare one amount to any other amount, just like you could when you're making a mole ratio in the past. There's, for every 10 hydrogen iodide, 5 iodine molecules are formed. So if I take this number and divide it by 2, it would give me my iodine change line. 0.02104. The next one has a coefficient of 2. That would be the exact same coefficient as the potassium permanganate, so the change line would be exactly the same. Then if we're looking at the next one, it has a coefficient of 1. So if I compare, it doesn't matter which one I compare it to, but if I compare it to the chemical right before, 1 is half of 2. So the change line for the potassium sulfate would be half the change line for the manganese sulfate. This would be 0.00421. And finally, the last one has a coefficient of 8. Again, it doesn't matter which one you compare it to, but once I've got a coefficient of 1, this would be 8 times as much water. So 8 times as much, that would be 0.337 moles. So all these are in moles. So what this is saying, we filled out the whole BCA table. We're just practicing using mole ratios to figure out amounts. And the change line, which is the coefficients, don't tell you how much you have at the beginning. They don't tell you how much stuff you have at the end. They tell you how much is used or how much is created in the reaction. So if we wanted to finish out the whole BCA table, I kind of look at the BCA table like a bunch of little addition and subtraction problems. Excess minus 0.04208 means you have leftovers. We've used all of our potassium permanganate. We're going to have leftover of the sulfuric acid. We have created some iodine, so at the end we started with none. Now at the end we have 0.02104 moles. We have 0.008415 moles of manganese sulfate. We have 0.00421 moles of potassium sulfate. And we have 0.0337 moles of water. Again, if I were just answering the question, I don't need to fill out the whole BCA table. I'm just trying to give you practice in using it. All we really needed to answer this question, we were comparing the amount of hydrogen iodide and potassium permanganate. So just using that 10 to 2 mole ratio would get us to what we needed. We now know for hydrogen iodide that there are 0.04208 moles of hydrogen iodide that would react with the 0.008415 moles of potassium permanganate. We want to know its concentration in molarity, which is moles over liters. You would know that you'd be able to measure, we calculated these moles, you'd be able to measure the volume that was used in the titration from the lab, and we were told in this problem that the volume was 0.204 liters. So if I take 0.04208 moles divided by 0.204 liters, that would tell us that the concentration of the hydrogen iodide was 0.206 molar, or 0.206 moles for every 1 liter. So there's an example of how to use a BCA table with a titration. Titrations really are just an application of stoichiometry calculations, so I don't look at it in my mind any different than I do any other stoichiometry problem.